All right, guys, we're going to start with sine and cosine, the main two of the three trig functions, and evaluating one more time. Been doing it for quite some time. And notice I also threw in the first quadrants boundaries, the 0 and 90. And then we have our big three reference angles. So you guys should know these by now, but let's make sure that we review. The way that we can do this quickly is starting with sine. We'll start at 0 with the 0 and then just increase by 1 all the way to our quadrant of 90, which would be 4. Now remember what we did last time was we called this pi over 6, pi over 4, pi over 3, and pi over 2 in radians. Either way, all right, it represents the same opening. Now remember, for cosine, it's the complement to sine. It's literally written in the word cosine. So we're going to go the other direction. And remember, I told you if you know this, it can cut your time in half. As long as you remember to take the square root of the top of each and every one of these. And those are all the values, which we shouldn't have to do this anymore. We should know that the sine of 30 is what?
1/2.
Good. And if we know the sine of 30 is 1/2, then we know the cosine of what is also 1/2?
Cosine of 60.
Very good, because remember, those are complementary angles, and these are complementary functions. That's when they're equivalent. So that means sine of 60, cosine of 30. Sine and cosine of 45 are all the same, as are 0 and 90, or 90 and 0. So what we're going to pose the question of in this new section that we're starting a new chapter of, what if we wrote these as functions of x and y rather than just sine of some angle and cosine of some angle, and getting out those ratios that we all love and memorize or haunt us in our dreams? What if we looked at all these values for not just the first quadrant, but one full revolution? Now, why only one? What's going to happen if we continue to move around and around and around? We'd get all the same values. And what if we thought of each input, which were our angles, and each output, which were our ratios, as an ordered pair, and actually graph them? What if, okay, that's enough of the what ifs. What if we just did all these things and saw what the result was? The cool thing is, if these are the values that I get for everything in quadrant 1, as we saw last time via the unit circle, what values are we going to get in quadrant 2? In quadrant 3? And in quadrant 4? They're all going to be the same as these. The only thing that may change is the direction, and therefore the signs of these things. So my friends, that is what 4 point 1 and chapter 4 is all about, and that is graphing. So if we were to look at this, and I'm going to do it very quickly, just so that we don't have to waste too much time here, right? But let's start at 0, and then we'll get to the 30, 45, and 60 degree angles. Then we'll get to the next quadrant, 90. And then what would be the 30, 45, and 60 in quadrant 2? Now that we've gone all the way to here, what would be the 60 degree angle, the 45, and the 30 till I got to the 180? Do you remember? $150, $135, and $120. Now, if I wanted to be correct in doing this in increasing order, I'd have to swap these two. Okay, but I'm looking at the reference angles being the same. Okay, so however you want to write it, no, then we would get to 180 degrees, and then we'd have the 30, 45, and 60 reference angles in quadrant 3 till we got to the 270. So what would be the 30, the 45, and the 60 in quadrant 3? Remember, that's the 210. Add 45 to that, 225, and add 60 to that, 240, until we got to 270. And you can see this is a lot, isn't it?
Mm-hmm.
Because now we're finally, look at all these values that we're going to have to plug in for sine, for our x, our angle, and evaluate it to see what we get out for our y, our ratios. What's the 30, 45, and 60 going to be in quadrant 4? Well, we'd have to subtract the 30, the 45, and the 60 from 360 to get those values. And what would they be? $330, $315, and $300. Here's the cool thing about every single one of these. You already know the 30, the 45, and the 60 for sine are what? We just reviewed it. What's the sine of 30?
Half.
1/2.
Very good. What's the sine of 45?
Square root of 2/2.
And the 60.
Square root of 3/2.
Beautiful. Well done, guys. Well, then guess what? Because I know that the 150 is a reference angle of 30, 45, and 60 for those, then guess what those values are going to also be?
The same as the ones we just did.
Absolutely, they are. And you could even color coordinate each one. You know, the 30s do all those, the 45s do all those, and then the 60s do all those. Whatever. As long as you recognize each and every one, this is going to be my 1/2, root 2/2, root 3/2. There's my 30, 45, and 60. So again, 1/2, root 2/2, root 3/2. And lastly, quadrant 4, my 30, my 45, and my 60. Again, reference angles. But remember, we talked about on the unit circle, if this was 1, 0, then we know sine is always the y over the r. And if we're on the unit circle, then that means r is 1, which means sine is equal to the y value of each and every one of these points. Well, then if we look at the height of each one of these, notice it starts at 0 and then it gets bigger and bigger and bigger until it gets to the biggest or highest point, which happens to be a what?
Quadrant?
A length of 1 would be the height of that. And then what does it start to do though? What do those y values start to do? Those heights start getting smaller again, don't they? Until it gets to 180 and it gets to be a 0. Then remember the x-axis separates the positives from the negatives. Well, now what happens as we keep rotating around to that 30, that 45, and that 60? What do my y values become now?
Oh, they become longer.
And in what direction?
Oh, negative.
Until it gets to the lowest or longest side, which would be a
-1.
right, because isn't that the point 0, -1?
Yeah.
Which again, look at my y value. That's what we said sine's equal to. And then it starts getting what again?
Positive.
Still negative. It's still down here below my
Oh.
x-axis, but it gets
Right.
smaller until it goes back to 0. So again, let me clean this up a little bit. And you can see for that 30, that 45, and that 60, we just said that the y values for the 30 would be 1/2 √2/2 and √3/2. See how they're getting bigger? Until they get to their biggest value of y, which is what sine's equivalent to on the unit circle, which is 1. Then what does it start doing?
Get smaller?
Very good. But again, we already know these values, right? The 30 is going to be the 1/2. The 45 will be the √2/2. And the 60 would be a √3/2. And again, what I mean by the 60, talking about the reference angle, dropping it to here, this would be a 60-degree angle. Even though we actually had to rotate to get to this point, how much? Well, if this is 180 to get all the way here, we just came back how much? $60, which means we would have had to have rotated 120 degrees. And again, with all of these points up here and the 1/2s, the √2/2s, and the √3/2s, what are we going to get for the 30, the 45, and the 60 in these two quadrants? We're going to get the same values, just like we talked about here. For any time there's a 30, 45, or 60, that's what we get for sine. It doesn't matter what quadrant we're in. The only thing that's going to change is positive, 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 1, positive, less positive, less positive, 0. But then that 30, 45, and 60 is going to be negative, 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 all the way to the -1. And then the 60, 45, and 30. Less negative, less negative, less negative until we get back to 0. So all this input, output stuff, what we're looking at is the graph of what we're going to call y equals sine of x. And what are we always putting in to a trig function? That's an angle. That's what x is representing. Well, then what do we get out when we put in that angle to whatever trig function? What are we always trying to give them out? When I tell you the sine of 30, what do you tell me?
1/2.
Good. So you give me out those ratios, those number values. That's what f of x represents, or y. That's just easier. So what we're trying to do then is take all of these values that we just talked about, including all of the quadrants, and we're trying to put them on an x and y axis. Because what's easier than saying all of this? Showing you all of this. And what did we say that is the easiest to typically do to a circle? Is to cut it into fourths. So what we're going to cut and do first on this graph is 1, 2, 3, 4 quadrants. And we can go in the negative direction as well. But what are we used to seeing on an x-axis? What do these tick marks usually mean?
1, 2, 3, 4.
Very good. And this would be -1, 2, 3, and 4, correct? Same thing in the y direction. But could I label this as 5, 10, 15, and 20 if I wanted?
Yeah.
Yeah, I could make my whole grid by 5s. I could even make this by 5s and this by 10s. It's our choice on how we label and show you. But because this is an x-axis and we're used to seeing this as real numbers, we're going to get rid of all of these weird degree measurements. And we're going to change them. Any guesses? Because it still has to be an angle.
To
What's the-
radian.
Very good. I was going to say, what's the other way we measure angles? It's radians. So instead of doing 0 degrees, 90 degrees, 180, 270, and 360 for our 1, 2, 3, 4 quadrants, what we're going to do is we're going to keep it real. And we're going to use radians to do that. So yes, we're going to still start at 0. As always, that's our origin. That's what we always originate or start with, is nothing. But then we're going to go in the positive direction. But instead of 90 degrees, we're going to put what instead? What is 90 degrees equivalent to in radians?
Pi over 2.
Excellent, Jacob. Pi over 2. Which means if this is what is called a quadrant, then if this is 1 pi over 2, what would this be?
2 pi over 2.
Which instead of writing 2 pi over 2, it's easier to just write pi. But the reason I'm saying it that way is if this is 1 pi over 2, this is 2 pi over 2, what's this?
3 pi over 2.
Very good. It's 3/90s. And then this one would be what?
2 pi.
Very good. 4 pi over 2s, which is easier said by 2 pi. Now, again, remember, we can go up and around positively, or we can go down and around negatively. Either way, we know that we're going by pi over 2s. And before we plot any and all of these points, ugh, that's a lot of them, right? Do you want to plot all those points?
Not really.
That's too much. I'm going to start with the quadrantal angles, because what did we just get done saying that sine is equivalent to? What is sine equivalent to? Always on the unit circle.
1.
It's y. The radius is 1. But sine, because it's always the y over the r, if our r is 1, then we know that sine is equivalent to the y value. Well, then look, at 0 degrees or 0 radians, we haven't made a rotation at all yet. What is my y value?
0.
So I know for a fact that if I was to plug in 0 degrees or radians, it's always a 0, right? Then what do I get out?
0.
Good. That's where my y starts. So I know 0, 0 is the first point. We start at our origin. But then what happens when we go all the way 90 degrees? What does my y value become?
1.
So yeah, I could plug in the sine of 90 or pi over 2 if it's in radians for my calculator, and guess what it would give me? We don't have to guess, we know. It's 1. So now I'm all the way up here. What happens when I go all the way over to the next quadrantal angle, pi, or 180 degrees? What did my y value become?
0.
So now when I plug this in, I go back to 0. How about 3 pi over 2? What does my y become?
Negative 1.
Now I'm down here, the negative, below my x-axis, and then we go all the way back around to 2 pi. What is my y value still?
0.
Just like where we started. And what's going to happen if I did this again?
The same thing will happen.
I'd start at 0, go up to 1, back to 0, down to -1, and then back to my original starting 0. But guys, does the graph look like this? Well,
Yeah.
what about everything in between? Don't we know those as well? Don't we know the 30, the 45, which is right in the middle of 90, and the 60?
Yeah.
What did we say the 30 was located at? A y value of what?
Oh, 1/2.
Yes. So I'm actually all the way up here, halfway between that 1 and negative, 0. What about for the 45? What was it?
Root 2 over 2.
Which I don't know what root 2 over 2 is, but I know it's bigger than root 1 over 2, don't I? So I know it's a little bit more. And then how about root 3 over 2 for my 60? I know that's root 3 over 2. So you can see, is it going to be a straight shot to that?
No.
It's actually going to have some what to it.
Curves?
Very good. Some curvature. Excellent, Jake. Now, guys, don't forget, what did we say would happen in quadrant 2?
The same thing?
And don't forget, we already knew that all of those 30, 45, and 60s in every single quadrant would give us the exact same values for y. And these are all going to be positive because y is positive above the x-axis. And these all would have been what if I graphed them as well?
Negative?
That's right, because that's what it means to be below the x-axis. Do you guys already see it?
Yeah.
These things to get from there to there and get back to my 0 are going to be positives. Where this to get down to this -1 and then back to the 0 are going to be negatives. And those 30, 45, and 60 ratios are going to be the exact same in every single one of these quadrants, which means we should now be able to graph what is called the sine wave or sine curve. Because we know these three things. And the fact that if we're on the unit circle, sine is equal to y. So we can go from 0 to 1, 0, -1, and then back to 0. And do we even need these now that we know it has that curvature? Or can we just plot these 5 key values? Would that be enough?
Yeah.
Good. It's enough for me. I don't need all of this ever again. I don't ever want to do that again. I'd rather just plot these 5 key points. Which, by the way, what are those 5 key points?
1/2. Or yeah.
They are my quadrantal angles. Those 90, 180, 270, and 360. But in radians. My 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, one thing that confuses people is like, whoa, why is there 5? I thought it was quadrantal angles. Well, remember, we have to start at 0, go to pi over 2, pi, 3 pi over 2, but we can't stop there. We got to keep going to get back. So that's where the 5th comes in to represent closing that circle, that loop. Now, don't forget, we could have also gone the negative direction, right?
Mm-hmm.
And if we did that, where would we still start?
0.
But then we would have went to what?
-1.
So going back pi over 2 would have taken me to the -1 value first. Then it would have gone to what?
0.
Good. Back to the 0 at -pi. Then what?
1.
Up to a maximum of 1, and then back to what?
0.
And notice, even if I build it in reverse, what do we end up getting?
The same thing.
The exact same thing. Because like we said, when we make one full circle, whether it was starting up or starting down, we would get the exact same values. So what we're going to do is basically just cut this. And we're going to talk about the period of time that it takes in order for this thing to repeat. And that is actually what we're going to call the period. What is the period of time that it takes for this thing to repeat? One full circle. Whether it's positive 2 pi or negative 2 pi, it takes one full circle to repeat itself. Makes sense though, right? One full circle. Because if I go again, it's going to be the exact same thing. It's the exact same circle. Okay. We're also going to call this other thing that's of importance to us, and that is the maximum height that this reaches, both in the positive and negative direction. Now, you know, everything originated from our origin, our x-axis, but how high up and low did this thing get?
1 and -1.
Good. So it went up a height of 1 and then went down a height of 1. So what do we usually call that when you're going real high up in the sky? That's usually in an airplane, right? What do they call that?
Elevation or altitude.
Yeah, there's the one I was looking for. So what we are going to call that in trig is the amplitude. And what would the amplitude of this thing be?
1.
It goes from the x-axis a maximum of 1 in both directions, both up and down, like you said, Jake. A height of 1. Okay, and that's the basics of sine. Now, I went all in with this explanation. I'm not going to do the same thing for cosine because you saw how long that takes. So rather than going through and plotting 0, 30, 45, 60, and then 90, and then every other quadrant for those reference angles, what do we say? Do those reference angles really help us to graph? Well, yeah, they definitely do, but what's enough to graph?
Just the 30, 60, 90,
Close.
or 45. What?
Just the quadrantal angles only, which we know this is the value 1, 0, 0, 1, -1, 0, and 0, -1. And we know cosine. If we write it like this, we know cosine of any angle is always equal to the what over the what? In general, what is cosine always equal to? What over what?
Oh, then y over r.
Close. Y over r is sine.
Oh, x over.
And if our r is a 1 everywhere, then we know that this would become a 1, and therefore cosine is equal to all the x values. So when I go to graph cosine, check it out. Let's label my 1, 2, 3, 4 quadrants in both directions. My y-axis, which were the highs and lows of ones, 1 and -1. But what do we say we wanted our x-axis to also be, since our y-axis is real numbers? We wanted this to also be real numbers, not degrees, which aren't fake numbers or imaginary numbers, but they're degrees. And they're a lot larger than if we were to put what instead for that first tick mark.
Pi over 2.
Good. And then what?
Pi.
Then what?
Pi over 2.
Good. And lastly,
2 pi.
in either direction. And because we know that cosine is equivalent to all the x values, then where are we starting at? Always along our x-axis in the positive x, and we like to rotate in the positive y. Where at 0 degrees or radians, when I put in 0 for my angle, what do I get out for cosine?
1.
Very good. It is 1. So when we plug this in, our input, our angle, we get out. For 0 radians or degrees, we get out a 1. There's my first point. 0, 1. Let's go to the next one. Pi over 2.
0.
Very good. Because as we mentioned, it's just the x values. And that's why we're not doing the 30, the 45, and 60, even though we should know the cosine of 30. Is that length of √3 over 2 for the x. Or the cosine of 45. That would be the √2 over 2. Or the 6. That would be the 1/2. All right, we should know those values, but it's easier to do ones, zeros, -1s, and zeros, isn't it?
Mm-hmm.
So plug them in. Let's just get these 5 points. When we plugged in 0, we got a 1. Then our x value became a what when we went to the next quadrant?
0.
Then what?
-1.
Then what?
0.
And back.
To 1.
Well, if you know these inputs, these angles yield these outputs, these ratios or y values, then you know the graph of cosine. It starts at what?
1.
We got that. Then it goes to what?
0.
Then what?
-1.
Then what?
0.
And back to our
1.
But of course, it's not going to be straight like that, because as we mentioned, if we did do the 30, the 45, and the 60, what is the cosine of 30 degrees or pi over 6?
Of 30.
Yep.
√3 over 2.
Very good. So that's up here. Close to 1, because I know √4 over 2 is 1. So √3 over 2 is about 0.8 something. So close. How about 45?
√2 over 2.
Very good. And then what about for the 60? What's the cosine of 60?
One half.
So as you notice, this is also going to have to, in order to get there, some curvature and not go straight there. You guys see that?
Yeah.
So since we know that, boom, 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 we can draw this. And of course, it's going to be that way for these as well. It'll hit that low point and then curve back up there. And what is it going to do if we went negatively instead? The exact same values, but in the opposite order. So 0, -1, 0, and back to my 1. So again, those things that we talked about, period of time that it takes to repeat, and the amplitude, the highs and lows. What is the period for cosine? Can you see it?
Pi?
Yeah, very good. 1 full circle. 0 to 2 pi. How about the amplitude? How high and low does it get?
1.
From
And then-
our x-axis, it goes up and down a highest and lowest of 1. That is the first section in a nutshell. Okay, now of course there's more to it, so I wanted to give you guys all the information there, but you can see they graphed each of these by doing some of the things that we just did. I did a little bit more. Then they add in the domain and range. Now remember, domain is all the input values. Talked about that last time. What can we put in? Anything, because the radius would be the only issue if it were 0. And we know that the radius cannot be 0 because then we don't have a circle. We're not dealing with triangles. This stuff doesn't exist. But the range of values that we get starts at a lowest value of -1, and we hit everything else all the way up to a highest value of what?
1.
So our domain for sine and cosine is anything from negative to positive infinity. Pick any value and plug it in. You will get something out. But will you get anything out? No, there are restrictions. So we say including -1, because that is a point on our graphs, and every other y value in between it and including +1. Okay, so the range of values that we get out are from -1 to +1, and we always like to list from smallest to biggest. So that's why it's negative to positive infinity, and same thing here for the range, smallest to biggest, -1 to +1. Other than that, there's a few more things that we could mention. Some of the X-intercepts and where they're located. Those are those zeros. And you can see for sine, it's at every pi or any pi. -1, 2, 0, or +1, 2. The period we talked about of time that it takes to repeat, 2 pi, 1 full circle. There to there, or there to there. Same thing here, or going to the left, 2 pi in either direction. Okay, the even odd stuff, don't worry about. That's more for calculus when you guys get there. All right, but what it means to be even versus odd, if it's a polynomial, it's a little bit easier to tell, but it has everything to do with what is called symmetry. Okay, and if it's even, then it's going to be symmetric with respect to the y-axis, meaning that if I was to cut along the y-axis and fold this over, there'd be complete overlapping with these two pieces. Where if it's odd, it's a little bit more difficult. Even, you're going to get the same thing about the y-axis. Odd, you're going to get the same thing, symmetric, but about the origin. So odd origin, even y-axis. Okay, meaning that if you notice, this is pi over 2, 1. Well, if it's odd, you got to do the exact opposite. You'd have to go negative pi over 2 and get negative 1. So that's what they mean by symmetry about the origin. Okay, not as useful. All right, so that's it for the first section. All we're going to do in this second section is move them around. So we're going to take what they call translations of sine and cosine. And we're going to start by graphing those 5 key points again. And again, I know it's quadrants 4, but the 5th one comes from closing that full circle. All right, and if you can graph those 5 key points for both sine and cosine, then you're good. All we're going to have to do is take those 5 key things and do any one of these 5 things. And that is shift it up and down, vertically we say, left and right, horizontally. So take the graph and actually move it entirely up and down, or left and right, or a combination of those things. Or we can actually vertically stretch, make it longer, or compress, make it look shorter. Or we can do that horizontally as well. Stretch it out longer this way, or compress it that way. And the last thing, vertical. Not usually horizontal. Every once in a while, they'll try to do both, but mostly what is called a vertical reflection. And you guys know in the mirror, you see a reflection. And if you move closer or further away, so does that weird looking person on the other side. Okay? Just joking. And what I mean by that is whenever we take a reflection, that distance from the mirror, which for us, if it's vertical, that is going to be our x-axis. So if we had, for example, a parabola, y equals x squared, then if I wanted all my y values to be the opposite, I'm actually going to keep it as y equals, but I would put a negative in front of the x squared to let you know, hey, keep squaring everything, but then take the opposite, which in turn is going to make every y value the opposite direction. And notice that is what is called a reflection about the x-axis, or a vertical reflection. But of course, we'll be doing that with sine or cosine, which if I'm dealing with sine, it would make all that go to the opposite side for my y values, and all of these go to the opposite side. So then we would have something like this instead of the original, like that. It moved to the opposite side for my y values, vertical. Okay, so the generic way that we will write these things is this. And each one of these variables other than x and y, which make it a function, are going to be the things that represent those 5 possible translations. Now notice there's only 4 of them, and you're like, wait, I thought you said 5. One of them is going to be for both. Okay, one will have 2 possibilities with it. And that is this special reflection piece. Okay. So I'm just going to give you the letters that associate with each one of those 5 things. And then we'll do a couple of quick examples, and that's it. That's why I spent so much time on the first thing. Okay. This, not too much to it. So the A is going to be what we deal with, what is called the amplitude. Okay. And the amplitude, remember, is how far up or far down our either sine or cosine functions went. So that is going to affect the vertical stretch or compress, right? So that will be the letter A. Now the vertical reflection will also have the letter A, but it will have a negative in front of the A. Okay, that's when we know that there is a vertical reflection, and it's going to affect my Y values because it's not in there with the X. Now I put trig in general because it can be sine or cosine of our angles. And if things are being done to that angle, it's not going to be one of our normal graphs. It will be a translation of it. Okay, so that's the first one. Let's go to B, which is the next one there. And B, as you can notice, is in with our angle X. All right, I'm going to make sure that you guys realize that X is the angle. And the Y is the ratio that we usually got out. The trig function, for now, will only be sine or cosine. Okay. But you know what always follows a trig function has to be an angle. And if stuff is being done to that angle, we want to know how it affects it. And when we multiplied by our trig function, we knew that that gave us a multiple for our Y values, that vertical stretch. The bigger the A, the bigger the stretch. The smaller the A, the compression it will have the effect of. And when I mean smaller, I mean fraction. Okay. The reflection will be when we have a negative. So the same goes with the B that's being multiplied to the X. And you have to make sure that you have the X by itself in order to tell me any of this stuff. Okay. So the A was our stretching or compressing vertically or reflection. The horizontal stuff is going to be in effect when there's an X value. Okay. And when there's an X value involved, then we know what? It's going to affect something horizontally. And if it's being multiplied, then we know it's going to be multiplying it and making it either stretch horizontally or compress horizontally. So that's what B will have the effect on. Okay. Well, then let's just go to the next one there. Let's do D and notice that it has a negative with it. Well, we know definitely it's done to the X. So therefore it's going to be horizontal. But notice it's a negative D. Because everything that's being done to the X is going to have the opposite effect. Right? I don't know if you guys had this issue. X's are X's because they wanted the opposite of us. Where Y's are Y's, we do exactly as they say. So when it says to multiply my sine by 2, that's what I'll do. All my Y values will now be twice as big. Or if it says to take 1/2, all right, instead of them going up to 1 and -1, I'm going to compress, shrink it down to be half as big for that amplitude. Okay, so I'll talk more about that, but anything that's being done to the x, you're going to do the opposite of, and anything with the y's, their y's, we're going to do exactly what they say. I'll make a note of that. All right, so the last thing that we have to talk about is the D there, or excuse me, the C, which, as you notice, they could have put it here, but they don't want it to seem like it's involved with the X stuff. So that's why they usually put it in front. And again, if it's a -2 or a +3, you're going to do exactly what that says to all of your Y values, which if you add 3 to every Y value, that is going to be a vertical shift up if it's positive, down if it's negative. So that will be the letter C. For the vertical shift. As for the X stuff, horizontal, horizontal. Okay. So I wanted to give it to you in a more written out form. So here it is. And again, notice one thing that is imperative is that you have the X by itself and the Y by itself for that trig function. And again, for now, just sine and cosine. Next week, we'll get into the other 4. Right? So that vertical shift we said would be the C. As is, whatever it is, Y's or Y's will do what it says. Horizontal, also known as the phase shift, will be the adding or subtracting to the X part. Horizontal, X-axis. And remember, we're going to do the opposite, and that negative there is how we represent the opposite. X's are opposite of whatever's being done. Y's are Y's, do whatever it says. Multiply, add to all the Y values. In order to find our amplitude, how far up or down we go from our original X-axis, that is going to be the letter A. Easy to remember, amplitude is the A, but notice I have the absolute values around it, because if there's a negative, then remember that's the one thing that has 2 possibilities. It could be a reflection about that X-axis, changing all of my Y's from positive to the opposite, negative, or negative to the opposite, positive. We mentioned the period of time that it takes for these things to be repetitive, and we said that would be 1 full circle of 2 pi. And then remember our 4 quadrants. We're going to call them quarters. All we do is take whatever the period is and divide it by 4. And you all know our quarters were by length of pi over 2. Okay, so that's all of it in a nutshell. If you guys want to do an example together, we can. Otherwise, we can just start working on our group quiz. It's totally up to you guys. Let me know. You guys want to do an example?
Yeah.
Yeah.
Okay. Now, again, I didn't just do sine and cosine like you did in the first section, because we already did that and I went in depth with that. So I started with a few things, just 2. And by 2, I mean, if I got rid of this stuff, do you see my y equals cosine x?
Mhm.
Do you guys remember the graph of cosine? I know we just went over it. Remember what we said cosine would be on the unit circle? If I was to graph this, I know cosine of any angle is always equal to the x over r. And if we're on the unit circle, then we're just looking at the x, right? And we know on the unit circle, where do our x's start at?
1,
And then they go to what?
0,
Good, because if I'm up here, I'm not left or right any. So it goes to a 0, then what?
-1,
Then what?
0,
Good, and then what?
1.
Back to 1. So if I know that, then I can lightly, and I'm going to do this lightly in a very light color. Let me mark my 1s here. My pi over 2, pi, 3 pi over 2, and 2 pi here. If they want however many periods, 1 or 2, you got both directions covered. But I'm going to graph just the original. Y equals cosine x in this light green. And we know it starts at 1, 0, -1, 0, and 1 in both directions. Remember, it's called the sine and cosine wave or curve because of that. So there's my original, which, if you guys can see, is all here. But there are some things being done. This -1 and this negative pi. So who can tell me what that -1 is going to affect and what that pi is going to affect? What is the -1 going to affect, the x or the y values?
Y value?
Was.
Very good, because it's not in with the x. Therefore, it's going to affect the y's. And what is it saying to do? Add or subtract 1 or multiply or divide by 1?
-1?
Yeah. So this is going to have a vertical shift of -1. I don't care that you know it's the C value. That's arbitrary, right? We just had to choose some letters, so we chose the beginning of the alphabet. Hey, you're going to know these values, A, B, C, and D, if they're given. Not always going to have all 4, right? You're going to know them, but they can vary, so that's why they're variables. So in this case, we have that -1, which all you need to know is that it's going to do this. I don't care that you know it's C. All right, then what about this? What is it going to affect?
The X?
Why are you saying that so high?
Just guessing. Oh, because it's paired up with the X. So
Yeah, there you go. You can see it's right there with the X. So since it's in the parentheses with the X, it's, yeah, going to affect the X. And again, is it adding, subtracting, multiplying, dividing, what?
subtracting.
And because it's being done to the X, we said that we're going to do the what with X's.
The opposite.
Notice with this, we did exactly what it said in the Y direction. But for this, it's going to be a horizontal, or what they like to call phase shift. We're not going to let it phase us. Of what?
Addition.
Good.
I, yeah.
Because it's the opposite for X's. So that means we're going to take all of our 1, 2, 3, 4, 5 key points, and we're going to shift them all what? Right pi. How do I know right? It's positive. We're doing the opposite, right? and then down 1. That's it. We are literally just shifting the original graph right pi down 1. What are we shifting right pi down 1?
The points,
Which points?
all of them.
Very good. That is very good, Jacob. All of them. Now, did we graph every single point on here in order to get this?
No.
No, we said that's too much work. We said we'll just graph these 5 key points, those quadrantal angles, in order to know the basic shape of this. So I'm just going to do it over 1 period. I'm not even going to do 2 periods. And I'm just going to take these 5 key points and do this to them. Which means, what are we going to have as our final look? Now remember, we get to say however we want for our tick marks. Well, it said that we had to shift everything right 1, and we know that we start at 0 normally to get this point. So if I move it right pi, what does that mean my first tick mark should be?
Pi.
Wouldn't that be cool?
Yeah.
Can I do that?
Yeah.
If I want to, but that means I'd have to make everything by pi, right? To keep it even. So maybe I'll just keep the way that I have it over here and just keep adding a few more. So I got my pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What would be the next one?
5 pi over 2.
What would be the next one?
3 pi.
Very good. 6 pi over 2, which would be 3 pi. Can I keep going?
Yeah.
If I want to, if I need to. I don't know if I need to. Actually, I do know if I need to. Because I know my starting point and my ending point. And what are we going to do?
Shift right pi.
Well, if I move this right pi, then I know this is going to be my starting point. And if I shift this right pi, then I know this is going to be my ending point. Do you guys see that?
No.
So I'm taking this graph right here, right? And I'm doing one of these things at a time. I'm starting with the right pi. And we said that we're going to move all of these points right a distance of pi. So we said our starting point is usually a value of 0, but we're going to have to add pi to that.
So you move it over 1 whole pi, which would, oh, okay, yeah.
So now my starting point is going to be here.
Yeah, yeah.
And my ending point, when I move the 2 pi, which was the ending point for these, when I add pi to it, it's going to become 3 pi.
3 pi. Yeah.
But I can't just do that. I also have to do a vertical shift of -1. So some people don't like to do both of these at the same time. They like to draw just small versions and do each step to the original. So they graph the original and then they'll vertically shift everything down 1, which means this point would move down 1, down 1, down 1, down 1, down 1. And when I plot those new points, look what just happened. Do you see how it just moved my entire graph down 1?
Mm-hmm.
Then they'll draw another one with that involved. And then they'll shift everything for the second thing. So I don't care how you guys do it. If you want to cut it into smaller chunks and not try to do all of it at the same time, I highly recommend that. Okay, especially until you get the hang of these things. Then when you start seeing how these move and what we're trying to accomplish here, then it's a little bit easier. So we know that we're taking these 5 points and we're going to move them to the right by a factor of pi and down by a factor of 1. So again, notice my 0, -1, 0. Here's my original. We're going to move all those down 1. So now I got this point, this point, this point, this point, and this point. Then we're also going to shift them what?
Right pi.
Very good. So now I'll take these and I'll shift them right pi. So that one would go there. That one would go there. That one would go here. This one there. And that one there. So my final graph, you know, it's hard to see with all of those. That's why I don't like doing all this at the same time, would look like this. Let's do one of these at a time. I'll go real light. I got 1, 0, -1, 0, 1. We're going to shift all those vertically downwards to become this, that, 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 and that. So I now have that graph.
Mm-hmm.
Then the last thing I'm going to do, I'll do it in that purplish color, was I will do the horizontal shift of pi. So I'm going to this one that I shifted down 1 everywhere, and I will shift it all right pi. So this 0 would come to here. This pi over 2 there. This pi, when I add 2 pi, or excuse me, a pi to it, I get 2 pi. The next green one was here. It's hard to see. Add pi to that. And last green one, add pi to 2 pi. You're there. So that would be what your final graph looks like. And how can you see it better? Get rid of all the clutter. Trying not to erase anything I want to keep. I'll keep that on there. So that's our final graph, where we took the original, moved everything right pi and down 1. So you can see instead of starting at 0 and ending at 2 pi, when I add pi to that, I'm now at pi and 3 pi. And instead of going up to a maximum of 1 and down to -1, I moved everything down, including the x-axis. Hopefully you can see that here. You can see my amplitude is still 1 and -1.
Mm-hmm.
There's my 1, 0, -1, 0, and 1 that we had originally. Everything just shifted down 1. So yeah, these are going to take some getting used to. But these are the types of things that we're trying to do slowly, one step at a time. Do you guys want to see one more?
All right, yeah.
Otherwise, we can start working on the group quiz, or you can do that on your own. But here's one more, which I'm going to save this until the very end. And I'm going to do a few little ones here until we're ready to graph the final. Because now you can see how many things are being done. One, two, and three. And I would argue that there's even four, but I'll show you what I mean by the fourth in a second. What's the most important part in graphing? Knowing what you're trying to graph. I'm trying to graph y equals sine x. Do you guys see it in blue there?
Mhm.
Well, then let's do a quick little sketch of what y equals sine x looks like. Draw my 4 quarters or quadrants, starting at 0, from 1 to -1. What do I know? What does the graph of sine look like? Remember, what do we say sine is always equal to?
Y over R.
And if we're on the unit circle,
It's equal to Y.
and where does my y value start at?
0.
Then it goes up to
1.
yep, then it goes back to
0.
and then down to
0.
right. We're looking at the y values in this ordered pair. This would be the
Oh yeah, -1.
1, 0, right? So we're just looking at the y values, which is why I'm only writing those. But you can see at this point, which I haven't rotated at all yet, I'm not up or down any. So that's why we say it's a height of 0. Then up here, I'm all the way up at 1, back to 0, down to -1, and then back to a height of being 0. So if you have that memorized, perfect. 0, 1, 0, -1, 0. Now I don't expect you guys to have that memorized yet. We just went over it. But you'll get there if you put the time in. Now that I have that, I got to do these few things. And what are these things? There's 1, 2, 3 things like you said. So I'm going to draw a few additional graphs in hopes that I can do these things one at a time. Which one of those things do you want to do first? 1, 2, or 3?
1.
I'm going to disagree with you and let you know it's not your fault. We don't just start at 1 from left to right. Remember the lettering system that we did, the A, B, C, and D. I suggest you go in that order always.
All right.
Get rid of the multiplying things before you do the shifting. Because when you start moving, adding, and subtracting things, it gets rid of your axes and can kind of throw you a little bit. Now, notice this number 2. Is it being done to the x?
No.
So it's going to affect our what?
Y.
Good. Now, notice there's a what with that 2?
A 3. Oh, a negative. Yeah.
Yes. And remember, that is going to be what is called a reflection, where this is going to change the amplitude. So if you can handle doing both of those at the same time, I'm down with it. But let's do number 2 first. How is number 2 going to affect our original graph? What is the negative going to do? And what is the 2 going to do? And like you said, Jake, we know it's going to be done to the y because it's not in there affecting the x. What does it say to do? Does it say add by -2?
No.
No, it says to multiply. And remember, y's are y's. We're going to do what it says. We're going to take all of our y values for our 5 key points, and we're going to multiply them by -2. What happens when you multiply all of these zeros by a -2?
It's still 0.
Beautiful. Just so you know, we haven't changed anything yet. These are still our 4 quarters, right? So all the zeros are going to stay 0. Well, that's easy. That means we only have to change what?
The ones.
By multiplying them by what?
-2.
And what happens when you take a +1 and multiply it by a -2?
-2.
Very good. That flips down here. And what happens when you take a -1 and multiply it by -2?
It's 2.
So then that flips up here. And that is now the graph of this thing with step 2 out of the way. Now
And that's with the reflection and the amplitude or whatever.
yeah.
Okay.
Yeah, notice that it's now up at 2 and -2. Now it doesn't look like it because of my grid not being the exact same, but as long as you label everything, I'm all good with you not stretching it out this big or that big. Don't worry about it. And do you see the reflection? See how all the positives went down, now they're negative? And all the negatives now flipped up and now they're positive?
Mhm.
So yeah, we took care of both of those things in one step. But I don't anticipate and expect you guys to be able to do all of these 3 things and give me the final without using a graphing tool, like a graphing calculator or Desmos or something like that. It's just slow it down, do 1 step at a time. And which step do you want to do next? 1 or 3? We already did 2.
Is it 1?
Remember, I suggest that you get rid of
3.
multiplying before adding or subtracting, because that's going to move this away from your axis. So yeah, I would do 3 next. Now, we said that the period of this is always going to be 2 pi, right?
Mhm.
From here to there, it's going to be the same. But when it's multiplied by pi over 2, remember, it's going to have the opposite effect. X's want the opposite of us. And what is the opposite of multiplying by pi over 2?
Dividing.
So we're going to take this and actually divide by pi over 2. But do we like dividing by fractions?
No.
So instead, we're going to multiply by its reciprocal. So I'll take that 2 pi and that pi over 2 and multiply by 2 over pi. So I'm going to go ahead and move this up a little bit so that I have my fractions separated and easily accessible. So the pi over the pi, the 2 over 2, all of that cancels out. That's why we did what we did. And here the pi's cancel out. So my new period for this thing is going to be what?
2? Oh, 4.
2 times 2, right? That's what's left. Everything else canceled out to be 1s. And why do we need to know the new period?
Wow, because that's gonna be our
So that we can cut it into our quarters, our 4 quadrants. And how do we always find our quarters?
the unit circle.
Take the period, whatever it is, because it can change, as you can see. And quarters means cut it into fourths. So what are our quarters now?
1.
So let me re-explain that, okay? Remember, our period is normally 2 pi, right? To get our
Mhm.
quarters, we take that and divide it by 4, which we know 2 goes in that, and that we get pi over 2. That's why normally we cut this into 1 pi over 2, 2 pi over 2s, 3 pi over 2s, and 4 pi over 2s. But now what we just found was that our period, because of this multiple of pi over 2 to the x, gives us a period of the pi's
4.
disappeared. That's good.
Mhm.
And when we cut it into fourths to get our quarters, we now have this, which means still going to make my 4 quarters, still going to start at 0, but now I'm going to go by, instead of a pi over 2, I'm now going to go by
1, 2, 3, 4.
beautiful. That works out really well. So now we've gotten this taken care of, that taken care of, and that. We didn't see it at first, but now we know it was 2 things. So what's the only thing left to take care of?
The 3.
You got it. So now we will take care of that. And what is that having an effect on? Is it being done to the x?
No, the Y.
And how?
Um, I don't know.
What is it saying to do? What is that 3 doing to our trig function? Adding, subtracting, multiplying, dividing, what?
Adding.
Very good. And since it's a y that it's affecting, we know y's are y's.
Do the same.
We're going to do what it says. We're going to add 3 to what?
Mm,
To that, and that. All 5 of our key points that we've done by graphing the first thing. This was the 3rd thing that we did or talked about doing, right? Now we need to do the
Mhm.
first thing. So that way we've taken care of all 3 of the additional parts to the original. And since I don't need, this is the last step, I don't need another one. I'm just going to do it for my last piece of this puzzle. I'm going to go ahead and just slide this over. I'm going to make my tick marks, which we said are going to go by what?
1, 2, 3, 4.
Just 1 unit. That's right. Instead of a pi over 2. And then our tick marks for that as well. Just because I know where this is going, let me shift this as well. Never mind, I'm not going to do that. I'm just going to raise it up. Okay, so Jacob, what do we have left to do?
Add 3.
We graphed the original. We did the multiplying of the y. We did the multiplying of the x. Now we just need to add 3 to what?
The 5 points.
And add 3 in what direction? The x or the y?
Y.
Very good. So instead of starting at 0, I will be at what?
3.
Very good. Instead of being at -2, I will be at what?
1.
Very good. My zeros are all going to be up at what?
3.
So in other words, when you add 3 to the y, my new x-axis, if you can see, will just be here. And do you see that -2?
Oh, yep, yep.
And that +2
Mm-hmm.
for our amplitude? Well, then there's your final graph, buddy. Now, again, I know it doesn't look a whole heck of a lot different, and that's because I didn't stay to scale the entire time. When you graph pi over 2 pi, 3 pi over 2, and 2 pi on a number line, like on Desmos, things like that, it's still just going to be 1, 2, 3, 4. But you know that this value pi is about what?
3.14.
So you know that this point right here actually would have been right here.
Mm-hmm.
3.14, like you said, a little bit more than 3. But because of this, we knew it changed it to actually work out really, really well. It got rid of that nasty number pi. So these do take time. They take time to get used to. That's why we just started off nice and easy with sine and cosine. So take the time that it does in order to get this down. And if you ever wanted to check, you can go to Desmos and type in things like this. All right, you can say, all right, y is equal to my sine of x. And there it is. But again, notice, what are my tick marks?
1, 2, 3, 4, and then on.
And notice, where is pi?
A little to the right of 3.
Yeah, I mean, I can zoom in on it. You can see that that's like that 3.14-ish,
Mm-hmm.
right? So that's where the other 0 is. Where's the other 0? That's a 2 pi. If you notice, 2 pi is 3.14 doubled. So that's the 6.28.
So yeah, 6. Yeah.
So that's the problem with using graphing calculators, is they don't change it to radians. But again, notice if I zoom out, you see it just keeps repeating itself
Yeah.
in both directions indefinitely. So what we're looking at is just one period, because we know that it repeats itself over and over and over in both directions. Right, so you can always check your answers on these things by just using Desmos, which is free. It's super simple to use. Graphing calculator, whatever, but that's why on the test, the exam, I won't be able to allow you guys to use things like that. Because it's a matter of you just plugging things in and you're not really learning anything.
Mm-hmm.
So sorry for the lengthy one today, but these things just take time to kind of explain and walk through step by step. If you guys have any questions, let me know. Otherwise, good luck. Work on this to understand it, not just get them done. That's going to pay dividends. And then we'll wrap up chapter 4 next week with all the other in 2 sections. They'll have 2 for each, all right, of the 2 sections: tangent and cotangent, and secant and cosecant.
Sounds good.
All right, guys.